To form a gas giant, it's simply about having a large enough core to have enough gravity to start grabbing gas and holding on to it. And that's it.
Once you've accreted a protoplanetary core that's maybe 10 or 20 Earth masses in size, you can now very rapidly start to grow much larger by drawing in the gas.
All of a sudden, things are falling in an almost uncontrolled way, a runaway gas accretion. And that's how you build a giant planet.
Core accretion should explain how all planets form. But when scientists try and apply the model to Jupiter, it doesn't work.
So if you try to build Jupiter's core, you run into a timing problem. So the time it takes to build a core big enough to form Jupiter, that might take 10 or 20 or 100 million years.
And it turns out that's too long.
As Jupiter is forming and starting to accrete all that wonderful hydrogen and helium, the sun is getting warmer and pushing all that material out of the solar system altogether. So as Jupiter's growing and feeding, it's like, hey, what are you doing to all my food?
The growing gas giant is in a race against time. The planet must fully form before its food runs out. Building a planet is no easy feat, with many tricky steps along the way.
Each one of these steps, going from dust grain to pebbles to planetesimals, takes a certain amount of time.
If Jupiter had to wait for distant rocks to collide and fuse, it would take 100 million years to form. And that's not possible, because our young sun attacks the gas in the protoplanetary disk.
A gas disk around a star can't last forever. The star is igniting and becoming active.
The clock is ticking. There's a young star in the middle, and young stars give off violent bursts of radiation, all kinds of solar storms, blowing away the cloud. So if you're going to be a giant planet, you have to move fast.
We know our protoplanetary disk only survived for about 4 or 5 million years. So we know that Jupiter was finished forming only 5 million years into solar system history. And that means we have to really jumpstart that process and get Jupiter to build a really big rocky core really, really fast.
Jupiter needs a giant core of rock and ice so it can grab nearby gas in the protoplanetary disk. The planet must rapidly build its core and capture this gas before it's blown away. To find out how Jupiter's formation was turbocharged, scientists turn to the Very Large Array in New Mexico.
Modern telescopes are really changing the game in how we study planet formation. They can observe protoplanetary disks in ways never possible before.
The Very Large Array peers 176 light years across the galaxy to a young star called TW Hydrae. The goal is to investigate the protoplanetary disk around the star using different wavelengths.
The observations that we have at different wavelengths can tell us what the disk is made out of to some extent. So when you look at an object in radio waves, you don't see the individual object, but you can observe their collective effect on the radio waves.
An individual pebble is too small for the array to see. But the wavelengths of the radio waves picked up from TW Hydrae reveal that small pebble-like objects make up the disk. But how can pebbles speed up planet building? To work out how Jupiter forms faster, we must wind back the clock to the earliest stages of planet formation.
So in our protoplanetary disk, we formed our first planetesimals, and we formed these out of all of the little pebbles that are out there in the disk. Now what? Still around its neighborhood and everywhere throughout the disk are a huge number of those smaller pebbles.
When we add these leftover pebbles to planet formation models, things go a lot faster.
Adding these pebbles to the mix, adding this to the models, was the big key.
These little pebbles can actually supply a lot of mass to these growing protoplanets. That's pebble accretion, and this is a method of actually accelerating the growth of early protoplanetary cores.
Now when a planetesimal forms, it no longer needs another planetesimal to grow. It can feed on the surrounding pebbles.
So this planetesimal has some significant gravity. It can start grabbing nearby pebbles and growing by accreting them. And this planetesimal has a huge reach because of how slowly these pebbles are drifting by. So it can reach way out and grab a huge number of pebbles really fast, and that'll enhance its growth rate. And this first planetesimal can grow really, really fast, eating up all the pebbles around it.
It's a feeding frenzy. By gorging themselves on pebbles, planets can grow around 1,000 times faster than with planetesimals alone. But when we use pebbles to model the formation of the solar system, something strange happens.
Pebble accretion, when we model it, it can be so efficient and so fast that if you just start with a disk full of pebbles and they start making planetesimals, each planetesimal could grow to be something like the size of the Earth, really, really fast.
Instead of forming giant planets like Jupiter, you'd form 100 smaller planets like the Earth, and this is clearly not what we're seeing. So there must be something else going on.
To understand how the solar system formed, we need to look at how the growing planets interact with each other.
So your first object in your disk that starts growing by pebble accretion is going to grow really, really fast. But the next object is trying to form from the same disk, the same pebbles, but it's growing nearby the first one.
As the infant worlds grow, their gravitational pull increases. Larger protoplanets bully their smaller neighbors.
This really big neighbor can perturb its orbit, can shake it up and down, and by lifting them up and out of the disk, they can essentially starve them, keep them from accessing all of those pebbles to grow.
Pushed out of the material-rich disk, the smaller protoplanet starves. The larger protoplanet thrives, gorging itself on pebbles. Pebbles help explain how outer planets beat the clock and grow large before the sun blows the protoplanetary disk away. By growing from pebbles, Jupiter and the other giant planets grew in just a few million years.
When we insert pebbles in our numerical models, our theoretical models, we can suddenly make these growth processes happen on those observed timescales.
Pebbles help Jupiter grow into the solar system's largest planet.
It can form the core big enough that it would very rapidly start to gobble up the gas around it and become the Jupiter that we see today.